All right, in this video, we're going to start on section 1.6, which is all about the natural logarithm. So suppose we're presented with the following problem. The population of Nevada in millions can be modeled by the following with t in years since 2000. So say we have this function and we want to solve for t when p equals 4. Well, if I plug 4 in for p, then what I want to solve for is going to end up being in an exponent. I want to try to solve for this value that's in the exponent, but how can I solve for something that's up in an exponent? So we need to develop something that will essentially help us undo this exponentiation. We need to be able to pull that exponent down. So we have the natural logarithm . So the natural logarithm of x, which is written as ln of x, is the power of e needed to get x. So remember that e is the natural base when we're talking about an exponential function. So that's the one that's used the most in contextual problems, is e to the x. So this is essentially saying that if we have the natural log of x equals some c value, that's going to mean that if we have e to the c, that would be equal to x. So that's what it means by saying is the power of e needed to get x. Now the natural logarithm is sometimes written also as log base e of x. Note that the natural log is not defined for 0 or negative numbers. So if you try to plug in 0 or something negative to the natural log, especially on a calculator, it will just spit out an error message. Now, if you know how to use other log bases, you know how to use log base 10, log base 2, log base 3, whatever. So you can have log base whatever number you want. You can have log base 5. You can have log base 2.7. That would be a bit silly, but you could. If you know how to work with different log bases and you're comfortable with that, go right ahead. Specifically for timing purposes, this class only covers natural logarithm because we can use it to solve any of the questions we want, even if we could also solve them using a different log base. But if you know how to work with other log bases and you're comfortable with that and you would like to use them, go right ahead. You're perfectly welcome to. Now we have some properties of logarithms, and they are the following. If we have the natural log of some a times b, now those can be anything, this can be rewritten as the natural log of a plus the natural log of b. If we have the natural log of a divided by b, note that these things are all happening inside of the logarithm. This can be written as the natural log of a minus the natural log of b. If we have the natural log of a to some power, we can bring that power down outside of the logarithm. This is the big important one for our purposes because we're going to want to solve equations that have the variable we want to solve for in an exponent. So this is essentially that step that allows us to kind of bring it down. And then we have that the natural log of 1 is equal to 0. The natural log of e is equal to 1. These three are a bit more important to remember. Actually, not really. These two included. So those 5 are the main ones that you are going to want to commit to memory. You are going to want to remember that they are able to be used and know how to use them. There are 2, they're not usually listed as the properties, but it's 2 kind of important pieces that happen with e and the natural log. If you have the natural log of e to the x, the natural log and the natural base of e essentially cancel each other out and just leave you with x. Same thing if you have e raised to the natural log of x, you also get x. So those 2 are kind of just like extra tidbits that you might want to know. But these 5 over here are the main pieces that you're going to want to remember. And again, this one that I starred is the one that we use most often because it's used in solving equations where the thing we want to solve for is in an exponent. So say I want to use these logarithm rules and I want to start to, so how we use these properties is essentially to expand or condense equations that have logarithms in them. So say I want to use the logarithm rules, the logarithm properties, to condense the following. So what I want to do is I want to use these things that I have up here to write this as, so I want to turn this into natural log of some one input. So I want to essentially condense this into one logarithm. Well, the first thing I notice is that I have a 3 and a 1/2. So I will write in purple over here. When you're condensing, you want to look at powers first, and then these two together are kind of the next step. So you look for powers first, and then you look from left to right. So left to right for the addition and subtraction. So I want to take care of these powers first. So let's go ahead and use that rule. And these powers are already outside. So I essentially have the right side and I want to go back to the left side. So I'm going to bring those powers essentially inside of the logarithm. So that will give me natural log of x cubed plus the natural log of y minus the natural log of z to the 1/2 power. If you want to change that 1/2 power into a square root, because those are equivalent, you totally can. I'm going to leave it as a 1/2 power for now. So now that we've got all the powers back inside, we're going to go ahead and go from left to right and take care of our addition and subtraction rules. So the first thing I come across is ln of x cubed plus ln of y. So since it's addition, that's going to condense into multiplication. So I essentially had this side and I went backwards. And now I have natural log of x cubed times y minus natural log of z to the 1/2. So since we have a subtraction going on, we have the right side of this rule, and we can go backwards to make this the natural log of x cubed y divided by z to the 1/2. And this would be our condensed answer using those rules. And so now say I want to go the opposite way. I want to expand the following. So if we're expanding, kind of use these rules first and then take care of the powers. So you kind of go backwards to the condensing step, which makes sense. So unfortunately, I have to scroll down past these rules. But so the first thing you should take care of, actually, so let me break this up even further. It's best to take care of the division first in the expanding steps. If you have, I should be careful there. I'm going to leave it like this. It very much depends on the problem you're presented with. So if you're presented with something like this, I'm going to take care of this division first. If it was something like 5x 2y over z, this is multiplied together, so I would take care of the multiplication first. So it's kind of like you need to see kind of the outermost piece of it. Is the outermost thing a division or a multiplication? So here we would want to take care of that division first. So since it's the natural log of essentially sub a over b, we're going to be able to split that up as the natural log of the numerator minus the natural log of the denominator. And now I'm going to go ahead and take care of any of our multiplication. So always take care of the division and multiplication steps before the power step when you're expanding. So I can break up this first piece still. I can break it up as natural log of 2x, sorry, the natural log of 2, I said I was breaking it up, plus the natural log of x. And then let's just leave it for now. Let's do one step at a time. So I broke, it was 2 times x, so we could break it up in terms of addition. Same thing back here, we have 2 things multiplied together. So we can break that up. Now we need to be careful there. This negative still needs to be connected to that entire piece, so we need to add on some brackets or another set of parentheses, but since I've got some parentheses floating around already, I'll use brackets. So we can split that up, but we'll need the brackets. Or you can distribute the negative right away. If you can recognize that splitting that up, but since they were both in the denominator, it would result in minus natural log of y minus natural log of z to the fourth. If you can just jump from here to there, that's perfectly fine. But technically what's happening is we're breaking it up with addition, but we had to keep that negative associated with that entire piece. So even though the original piece of natural log of y z to the fourth got broken up, that entire piece that now becomes two pieces still has to all be under the negative, if hopefully that makes sense. And the last piece here is then to take care of any powers that you have. So the only power we have is in the z to the fourth term. So we have natural log of 2 plus natural log of x minus natural log of y minus 4 natural log of z. And this would be our expanded step here. So I'm going to stop there. This is about 1/2 of the way through 1/6 notes. We're going to finish 1/6 notes on Wednesday, but this is essentially the start of natural logarithms. What we're going to do next is we're going to find out how to actually solve with these. So that's when we're going to be pulling in this very important power step that I noted. So we're going to be using that a lot on Wednesday to be able to solve equations where we want to get into the exponent. So let me know if you have any questions about the 1/6 material, and I will see you all on Wednesday.